So as Francisco said, this first session is about search and ranking. And our first speaker is Niazadeh from Chicago, presenting work with Mohammad, Reza, Aminian, and Vahideh Manshadi. So I invite you to come up, Rad. Thank you very much.
All right. You know, it's good to start early sometimes. Thanks, everyone. Thank you so much for coming to my talk, and thanks to the organizers for the great conference. It is actually my first time attending IMO, so I'm very excited to catch up with some old colleagues and meet new ones. So I'm Rod. I'm from University of Chicago, and I'm going to talk about this recent work with my PhD student, Mohammad, Reza, Aminian, the gentleman on your left side, and my good friend and colleague, Vahideh Manshadi. So this paper is about coming up with a framework for Markovian search with costly inspections in the presence of socially aware constraints. I'm going to explain all of these terms throughout the talk. Right. So the main motivation of this work is really thinking about algorithmic hiring, and when different organizations and firms, they try to use automated systems in order to perform two tasks, in particular screening and hiring. And they use these tools mostly because of the fact that they are faster, more efficient, and also can capture certain limitations of this type of problem. For example, if there's a limited number of positions and you want to hire for that, then these algorithms they can capture. But also, especially in a high-stakes context such as hiring, one important aspect is trying to be non-discriminatory towards different demographic groups. And these algorithms, at least they don't have explicit bias, so there is no line in the code that says, hey, discriminate against certain minority group. But as we all know, the literature in algorithmic fairness is suggesting that now the issue is going to be hidden somewhere else, and the input to these algorithms are going to be, in some sense, biased. So focusing in this context, this form of implicit bias, they exist because of the bias in the data that these algorithms use in order to get trained, and also bias in the input through the screening processes. So when we are eliciting CVs from candidates, sometimes these information acquisition procedures might be biased. All right? And there are many ways that you can try to address this question. So one common approach is the following. So we try to calibrate the outcome distributions generated by these algorithms in order to make them non-discriminatory. And if you're wondering why do we want to do that, so there are many ways you can think about non-discrimination in contexts such as hiring. One view is the egalitarian view. It's a good thing to do. You know, as a society, we want to make sure that our systems are inclusive and no one feels excluded. But at the same time, if you're even a utilitarian and you're thinking about really like maximizing the efficiency of hiring, many times there is unobservable signals about candidates that can only be observed if you give them the opportunity. So if you want to maximize with respect to these type of longer-term outcomes, again, making sure that the system is unbiased and non-discriminatory can help. And one approach to do that is by imposing what I call ex-ante on average constraints. So these are certain constraints on the outcome distribution generated by these algorithms, and they're going to make sure that certain criteria are satisfied. So you can think of different notions of group fairness. For example, I have two demographic groups. I will make sure that the likelihood of both of them getting a job is high enough. You can even think of like individual fairness at an individual level. I want to make sure that each individual has enough chance to be interviewed or be hired by the firm. And then these ex-ante constraints can also incorporate various operational constraints, for example, budget constraints on average, or you can think of different forms of diversity criteria that can be captured by this constraint. I'm going to formalize them throughout the talk. So the high-level research agenda is coming up with a Markovian framework for sequential search. So I'm mostly focusing on the context of sequential hiring. You should think of a tech company hiring software engineers year-round, so it's pretty much a sequential process. And the question is how we can impose different ex-ante constraints that are achieving a certain socially aware objective in the search. So now, from now on, it's purely a computational question. So how can we impose these constraints and how we can design algorithms that they perform the search, maximizing the utility of the searcher, in this case the firm, while respecting these on-average constraints. So for the purpose of this talk, I'm going to actually focus on a very, very special case known as the Pandora's box problem. Goes back to the beautiful work of Weitzman in 1979 on optimal search among alternatives. But in the paper, we are really thinking about the generalization to a problem I call joint Markovian scheduling, which I'm not going to detail that much, but I'm happy to talk about it after the talk. All right. So what is Pandora's box problem? It's kind of a very interesting fundamental question in theoretical microeconomics. And this is the setting. So imagine I have n candidates. For the purpose of this talk, I'm going to assume that these candidates, they belong to one of the two demographic groups denoted by X and Y. So each candidate has some unknown quality. So think of it as the valuation, or think of it as maybe a skill of that candidate for a certain job they are applying for. And these qualities are unknown, but they are drawn from common prior distributions denoted by Fi. And then the searcher is going to interview these candidates in a certain order that is decided by the searcher himself. And then upon interviewing a candidate, the searcher should pay a cost, that's the inspection cost, and then we'll realize the actual value of that candidate. And now the question that the searcher is trying to find to solve is that how to find a feasible policy, maybe randomized, maybe deterministic, maybe adaptive, maybe non-adaptive, that maximizes what I call the utility of the searcher, which is the value of the final candidate that the searcher is able to identify, minus the total cost that the searcher is paying along the way to identify that candidate. And I'm assuming that the searcher is just hiring one candidate, but you can really think of extensions of these to other exposed feasibility constraints. But for the purpose of this talk, I'm just going to focus on hiring one person. So we try to hire one person, and on top of that, this searcher is trying to satisfy another extra constraint, which is not a constraint that you should that is considering the vanilla Pandora's box problem, and that's what I call the demographic parity. So imagine that I want to equalize the expected number of candidates that I'm hiring from each group, and in this case, basically equalizing the probability of hiring across the two demographic groups. And the question is how to do that. All right? So first of all, if we don't have that constraint, what would the optimal policy look like? And that brings me back to this classic seminal work of Weitzman. And there is a beautiful index-based, what I call an index-based policy, that's an adaptive policy and maximizes the utility of the search. Let me tell you briefly what does this policy do. So there is this notion of reservation value, sigma I, that you can define for a box for each candidate. So the reservation value is basically the unique number sigma I, such that the expectation of the positive part of Vi minus sigma I is equal to the cost of inspecting that box. So you calculate these numbers once for boxes, and here is what the optimal policy would look like. So you have to go through these boxes in the decreasing order of the reservation values, and you should keep opening the boxes. When I say open a box, this is equivalent of interviewing the candidate. So you interview the candidate, and then your search is going to stop at some point, and that point is when the value that you have seen, the largest value among all the candidates that you interviewed, is exceeding all the remaining reservation values. At that moment, you stop and you pick that candidate that has the largest value. So it turns out that this is actually optimal among all the possible adaptive policies, which is exponential size of state, a space. And this is great, but let me actually run it on a simple example. So this is the example you see on the slide. So I have 4 candidates, 2 belonging to group X and 2 belonging to group Y. I run the Weitzman policy, and here's what I get. So the probability of selection from the two groups, they're going to be very different. So in particular, for one group, it's around 0.8. For the other group, it's around 0.2. And this policy obtains some expected utility. Of course, adding any constraint is only lowering down the expected utility of the searcher. But maybe we can actually lower it down a little bit and be much more fair across the two demographic groups. So now, let's think of the other extreme. So I don't care about the utility, I just want to be fair. So here's one trivial solution. I can flip a coin. With probability half, I do my search optimally in group X. With probability half, I do my search optimally in group Y. And of course, in this way, you are equalizing the selection probability across the two groups. And then you can calculate the expected utility. It's going to be much lower than the expected utility of the optimal policy, but it's going to be fair. And the question I'm asking is, can I do better than this? Can I actually be optimal in terms of expected utility and at the same time satisfy this expected demographic parity constraint? And here's a simple idea. So you have these on average constraints. We are solving some complicated stochastic online optimization, but you have a constraint. You can Lagrangify that and bring it to the objective. So let me introduce some notation. So AI, think of it as a random variable given a policy indicating whether you select a candidate or not. And I think of it as another indicator random variable that indicates whether you interview a candidate or not. So then my objective function, given a policy pi, can be written down in this linear form. So it's going to be summation of AI vi minus summation of II ci. And then let's say I Lagrangify my constraint to the objective. So the Lagrangian has a nicer form, so I can actually merge these terms into the actual objective function. And now let me try to maximize over all possible, maximizing the Lagrangian over all possible policies. So that defines the function g lambda that you see on this slide. So this is actually kind of a nice function. So it's going to be piecewise linear. It's going to be concave. And then you can try to optimize this function. In particular, one observation is that if I give you a certain lambda, you always have a polynomial time access, query access to this function. Why? Because given a lambda, if I look at the form of the Lagrangian function, this actually has the same form as the original problem. You only need to adjust some of the values. So you need to adjust the values in group X by lambda, and adjust the values in the group Y by minus lambda, and then you need to solve the optimal policy. So you have query access to this function. And then the funny thing is that if I think of this optimization problem, I want to have first order access to this function, to the gradient of G. That also is kind of like easy, because by applying envelope lemma, you can say, hey, if I, given a lambda, if I find the optimal policy after adjustments, and I look at the slack in the constraint generated by that policy, that gives me query access to the first order derivative of this function. Okay, so now we can try to optimize. And let's say I go after this convex function and find a minimum point lambda star. If I'm lucky and this lambda star lands on a flat interval like this, then the derivative is going to be 0. So for any lambda, this objective, this is just one-on-one optimization, is an upper bound on the expected utility of any policy. And then if this term is 0, then you're lucky, so you actually identify the optimal policy that satisfies your constraint as well. So if there is a situation like this, then there is actually the deterministic policy that is just adjusting the indices in some sense. Basically, you adjust the problem instance, you run Weissman policy on top of that, and that's going to be optimal. But in fact, this is a degenerate case. Most likely, what happens is you end up at the breakpoint. So you will have a lambda star, which is in this situation. And now, given the lambda star, I'm going to adjust my instance as before, so try to solve the Pandora's box problem with adjusted values. And it turns out that in this case, there will be ties in the order. So many times you're going to, OK, so this adjustment is equivalent of adjusting both the sigmas and values. So trust me, this is the proper adjustment. And then when you try to run the Pandora's box optimal algorithm for this adjusted instance, it turns out that you need to take care of some ties in the order. There might be ties between reservation values. There might be ties between values and reservation values. And you need to break these ties. So here are two questions. Question number one, does there exist a tie-breaking rule, in particular randomized tie-breaking rule, that can basically satisfy the ex-ante constraint? And when you think about that, there are exponentially many options. So in principle, there might be even a distribution over exponentially many different policies. So the second question is, does there exist, say, polynomial number of permutations or policies that if you randomize over those, you can satisfy the ex-ante constraint? All right? So turns out, for this special case, the answer is actually quite easy. So there are going to be two possible randomized tie-breaking, two possible tie-breaking rules. If you randomize between the two with certain probabilities, then you're going to be the optimal policy that satisfies the ex-ante constraints. And the proof is really like a few lines. So think about this situation, and let's say I perturb lambda a third a little bit to the right and left. So by two perturbations, infinitesimal perturbations, you're going to still be in the world of optimal adjusted policies. One of them is going to have a slightly positive slack, and the other one has a slightly negative slack. In fact, these two policies are those that among all the optimal adjusted ones will maximize the slack and minimize the slack. Now, we can think of what are these policies. So these are what I call group preferred rules. So the tie-breaking rule corresponding to lambda star plus epsilon is basically the one that prefers x over y all the times. And the other one is when you prefer y over x all the times. It turns out that with these correct probabilities that depend on the slack of these two, what I call extreme tie-breaking rules, you can satisfy the constraint exactly. And this is essentially going to be the optimal policy. So this is the optimal policy. And when you compute expected utility, it's going to land somewhere between the naive policy and the actual optimal unfair. Now, what would happen if I, for example, give you a general affine constraint of this form? For example, you might want to satisfy a quota constraint. You might want to have a budget constraint on subsidies for interviewing candidates from an underprivileged group. Still, the same technology is going to go through. This time, you might want to adjust both the values and cost. But essentially, the extreme tie-breaking rules can extend. You can think of situations where I'm going to refine my constraints so that I'm targeting certain quantiles of the population. So I don't want to equalize the likelihood of hiring between the two groups. I want to equalize only if they are among the top candidates. So for this refined constraint, again, the same technology would go through. There is going to be a slightly different adjustment, but essentially the same technique will give you a way. And there is an extension, more complicated extension of the extreme tie-breaking rules for these refinements. All right? Now, what would happen if I give you, let's say, two affine constraints? For example, I want to equalize the likelihood of selection, and I want to have maybe some expected budget on a screening. I want to make sure that I'm not interviewing the expectation more than 10 candidates. You can now define two Lagrangian multiplies, lambda 1, lambda 2, Lagrangiify the constraints. So everything I said essentially goes through. There will be a G lambda function. You have polynomial access to this function. It's going to be piecewise linear, convex, everything nice. So one question is, does there exist a randomized tie-breaking rule after minimizing this function at the point of lambda star that among the adjusted index space policies will give you the optimal constraint policy? The answer is yes. This is kind of like related to feasibility of stochastic optimization problems. Another question is, does the idea of extreme tie-breaking rules extend? Basically, can I still think of four policies by looking at lambda 1, lambda 2 plus minus epsilon, and these epsilons are going infinitesimal? And this time the answer is no. So it turns out that even with two constraints, I can cook up examples in which if you look at these natural extreme tie-breaking rules, then you won't be able to satisfy the constraint exactly. The figure that you see here is kind of a two-dimensional figure for a slack of the two constraints. So 0, 0 is the target point. And then if I move along perturbations like these, plus minus ones along each dimension, then I'm going to end up with three slacks like this. And the convex hull is not going to include 0 this time. However, if I move along all the perturbations, so there are infinitely many of them. If I move along all those directions, there should be different policies, maybe exponentially many policies, that if I randomize among them, then I will be able to achieve 0. This is now related to what I call Kara-Theodori problem. So in some sense, if I can define a polytope, which is a polytope of all the slack in the constraints. So it's like the d-dimensional polytope where d is the number of constraints that I have. And you can basically say what's the space of achievable slacks by some optimal adjusted policy subject to some tie-breaking rule. And the question is, can I solve Kara-Theodori in this space, which is exponential size space? So the first question is, well, first of all, I know that there should be d plus 1 policies The question is, can I detect them? The answer, I don't know. I don't know if the D+1 policies are detectable. But we have an algorithm which is based on running ellipsoid in some dual space that can identify actually polynomial many policies that if you randomize among them, then you can satisfy the constraints. All right. But if I have a convex constraint, and or if I want to have a faster algorithm, this technique does not work. But we show in the paper that there are ways that you can use learning in games by kind of playing a primal dual algorithm between the primal player who is picking policies for the Pandora's box problem and the dual player who is deciding on the choice of these Lagrangian multipliers that will be near optimal and near feasible. Again, I don't have time to go over the details. One thing I want to mention before I conclude my talk, so we extend all of these results to this problem called joint Markovian scheduling, which can capture more sophisticated searches where there are multiple stages for the search, or maybe candidates, they can reject offers, etc. So you should really think of basically each candidate as a Markov reward process, and you can play with these Markov reward processes throughout time. We have numerical simulations, which I won't have time to go over, but the upshot is that essentially in more practical situations, there is not that much loss by imposing these fairness constraints in terms of the short-term utilities. And if you think of like really like long-term utilities, we have these models that they show that there is a gain for fairness, even if you impose these constraints. I'm happy to talk about them offline. And that's it. Thank you so much for your attention.
Hi, thank you for the great talk. I had a question about the different constraints you might be able to impose. Do you get slightly different results, or have you looked at different types of constraints aside from demographic parity? And I wonder if some of them may interact with each other, may cause further computational issues, for example.
Excellent. So in the paper, we can capture basically any set of affine and convex constraints. But what does the resulting policy look like? Usually, these tie-breaking rules are going to be very complicated. Even if I have just one affine constraint that doesn't have the form of demographic parity, there is a scoring rule that we introduced in the paper. It's kind of an adaptive scoring rule that will give you the right tie-breaking. So this is random as a scoring rule. They don't always have a natural form to describe. For the demographic parity, it's actually very easy to describe. But if you just want to even equalize the expected number of interviews across the two groups, even that constraint will give you very complicated randomized tie-breaking rule. For the case that you have one constraint, there is just like tie-breaking rule across two policies. So basically, you need to flip a coin once in some sense. But if I have like D constraints, then we have polynomially many policies. We don't know what do they look like. It's not really like interpretable that much. But it's a good question that can be find interpretable policies here.
Okay. Let's give another round of applause for Rod.
Thank you.